Greetings, chemists. Last time we talked about how we can use quantum theory to map out where electrons reside within an atom, and how to show that they fill different shapes of orbitals at different energy levels. And let's go further with that today. We talked about, for instance, that if you looked at a nitrogen atom, nitrogen had 7 electrons, and it became a 1s2, 2s2, 2p3, were the places where those electrons existed within its orbital structure. Okay? And similarly, we could do something, let's take phosphorus, for instance. We find that phosphorus is a 1s2, 2s2, 2p6, 3s2, 3p3 element. Okay? Certain chemists and scientists in the past looked at nitrogen and phosphorus before we had even developed quantum theory, and they noticed similarities. They noticed, for instance, that nitrogen, if you put it in a stream of chlorine gas, you can get chlorine atoms to stick to the nitrogen, and you can show that 3 chlorine atoms have to stick to a nitrogen to form a bond. Well, they tried this experiment with phosphorus. They put a sample of phosphorus, and they reacted it with some chlorine. They took some chlorine gas, and what they found at the end is that the compound that it created was phosphorus trichloride, with phosphorus attached to 3 chlorines. They said, how interesting. Whether it's phosphorus, whether it's nitrogen, they both stick to 3 chlorines. Okay? And that this is not unique to just those two. So let's take a look at some atoms. Let's take a bunch of different chemicals and react them with chlorine. If you do it with lithium is a very light atom. And if you react it with chlorine, it becomes lithium attached to 1 chlorine. If you take the next heaviest element after lithium, the next heaviest element after lithium is beryllium. If you put beryllium into a stream of chlorine gas, what you get is beryllium attached to 2 chlorines. And if you keep going, boron is the next heaviest. You would get boron. Boron will stick to 3 chlorines. If you go next is carbon. Carbon, I didn't leave myself any room, but carbon will stick to 4 chlorines. Nitrogen will stick to 3 chlorines. Oxygen, which is the next heaviest, I'm just going by atomic mass here. Oxygen will stick to 2. Fluorine is the next heaviest, sticks to 1. Okay, now there is another element there, neon, but we leave it out at this point because we're in history, neon and the noble gases were discovered much later than a lot of these other chemicals were. Okay? If you keep going, you will find an element after neon called sodium, and sodium sticks to 1 chlorine. And if you go past sodium, you get to magnesium, and it sticks to 2 chlorines, and it looks like the pattern repeats. And it does. If you go to aluminum, it sticks to 3. And so 1, 2, 3, 4, 3, 2, 1 seem to be this interesting pattern. And it allowed people to make certain predictions. For instance, if you keep going in atomic mass, there should be a chemical that is heavier, let's say, than silicon. Silicon would be back here. Silicon sticks to 4 chlorines. Well, there should be an element even heavier than silicon that also sticks to 4 chlorines, and it should come right after gallium, and it should come right before arsenic. But at the time, I'm talking a couple hundred years ago, no one had seen such an element heavier than silicon that stuck to 4 chlorines. But it was predicted, and this guy, Mendeleev was his name. He was a Russian chemist. Mendeleev said, I predict that this chemical will eventually be found. You start looking for it, and he made a name for it. I think he called it ecosilicon because it was below silicon. And so eventually people found this element, and it had all of the properties that he predicted it would, like what kind of mass would it have, etc. And so this idea that these things repeat in a regular order had some value. And when you look even closer, okay, I had to pause there and come back to the video, so there's going to be a break in there. Essentially, when people saw this trend that it was happening frequently, where we go through these 7 and there's 7 more, and then the pattern repeats, they call it a periodic repeating trend. They noticed, well, look at one of the reasons may be, later on they noticed this, that nitrogen and phosphorus have similar electron structures, that the outermost electrons are in the p3, and so they are also here in the p3. So what we do is we try to draw, and I'm going to use a whole page for this. We try to draw it out. We notice, for instance, that if you were to take and put hydrogen here, okay, he has a similar chemistry. He will stick to 1 chlorine as lithium. And then beryllium sticks to 2 chlorines. And then you have boron sticks to 3 chlorines. And then you have carbon sticks to 4 chlorines. And then you have nitrogen sticks to 3 again. Oxygen sticks to 2. Fluorine sticks to 1. And then it repeats. So you go back and you say, all right, well, sodium sticks to 1 chlorine, and magnesium sticks to 2, and aluminum sticks to 3, and silicon sticks to 4, and phosphorus sticks to 5, and sulfur sticks to 6, and chlorine will actually stick to itself once. And then you go back, and if you go down to the next ones, you get potassium sticks to 1, and you get calcium sticks to 2, etc. And then there becomes a problem, because the next heaviest element after calcium is scandium, and we find that scandium and titanium and vanadium, which are the next ones in sequence, don't quite follow the same pattern. But if you go farther enough along, you do find ones that go with the same pattern, like aluminum. The one of gallium. Gallium is actually should be the next one in line under aluminum, but there's like 10 elements in between it. So they split this thing apart and they write it like this. They take lithium, beryllium here, right? And they make a big gap, and then they put boron and carbon and nitrogen and oxygen and fluorine here. And then they can do sodium and magnesium, big gap, and then aluminum and silicon and phosphorus and sulfur and chlorine here. And then when they get down here to potassium and calcium, they find a completely different pattern for this section. So this section up to here, they find a bunch of metals that have certain patterns, and you can write them in, like scandium, and you can write in titanium and vanadium and chromium and manganese. I'm going to run out of room, aren't I? Iron, cobalt, nickel, copper, zinc. Cobalt, nickel. I ran out of room. There should be 2 more, copper and zinc. Pretend that one is not underneath aluminum. That's my bad spacing. Don't do that. Well, what you find is that if you keep going by mass, right, these next 5 or 6 in line match up right along here. And remember, he had a gap. Mendeleev said there should be one here underneath silicon. They hadn't found it yet. When they eventually found it, it was eventually called germanium. But at the time, there was a gap in that repeating sequence of things that, in this case, added up to 4 chlorines when they bonded with it. But underneath these metals, there was a whole nother set of 10 metals that did react basically the same way as those metals, but not quite like the pattern you saw over here. So you would get, I'll do a couple of them, like yttrium and zirconium. And you can keep going down. And eventually there was a row down here where we had to spread it out again. So what you're looking at is this. This is the sum total of all of the elements that we, at least at this point, the point that this book was written, right? You can see some of these are empty, but I think some of them have been discovered since then. And look what they did. You can actually see that here. So you have the first one being hydrogen, and then lithium, beryllium, and boron, etc. And then they put the transitions in here because these guys don't quite react in the same pattern as those, that 1, 2, 3, 4, 3, 2, 1 that we were looking at here. And then if you keep going row, 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 you find these guys, the lanthanides and the actinides, that should technically be inserted here because they follow a different pattern even from these transition metals. Okay? But the pattern of these on the lanthanide side, right, every one on top reacts pretty similar to the one directly underneath it. That's the patterns on this periodic table, that in some vertical column, you will probably be able to stick to the same number of chlorines. Okay, and there are other things that we see chemically that are similar, but that's an easy one to think about, is numbers of chlorines that you might stick to. So we call it the periodic table of elements. The periodic nature just refers to the fact that they've been organized according to other similar elements in their vertical columns that react very similarly. Okay, and what we can then go on to talk about is that if you look at those electrons as we had defined them before, lithium is a 2s1 outer orbital. Sodium is a 3s1 outer orbital. Potassium, which is right underneath it, is a 4s1 outer orbital. And the reason that they probably all react similarly to chlorine is because of that outer electron structure. That if you look at my original here where I have the oxygen and the sulfur, oxygen is a 2p5, sulfur is a 2p6. Okay, and so the reason that they probably react very similar to each other, stick to the same number of chlorines that is going to be related to their outer electron structure. So a lot of the chemical properties we see on the periodic table have to do with their electrons, and so that's why we organize the periodic table the way that we do. So, what else can we do with this periodic table? I'm going to draw, again, a brief periodic table here. Let's see if I can even subdivide it. So that should be 3 each. 1, 2, 1, 2, and like that. And then, of course, there's this bit down here at the bottom. And this keeps going, of course. Now, let's say this is a pretty quick and dirty periodic table. You probably noticed that when I drew my periodic table before, I really didn't look very much at these guys, the helium, the neon, the argon, the krypton, the xenon, and the radon. Sorry, that's Rn. I always confuse that one with radium. And the reason I didn't get into those is that, one, we call them the noble gases. That's column 8 on the periodic table. And they were discovered much later. And the reason they were discovered is they don't stick to chlorine at all. And they also don't form bonds very easily, hardly at all. Some of them near the bottom will form bonds with a lot of energy. Like you could force it if you were really cramming them in there. But helium and neon basically don't form any kind of connection with any other atom. And so you wouldn't see, for instance, you wouldn't find them in like a rock somewhere. So if you dig up rocks, there are oxide minerals where oxygen sticks to pieces of the rock, or fluoride minerals. You would never find a halide mineral. Helium can't stick to other elements the way certain, everybody else can. So it took a long time to discover them. They seem to be very stable. They don't seem to go out of their way to react with anybody else or combine with anybody else to form some kind of compound. And what the reasoning the reasoning of chemists is that they have filled all of the electrons on their energy level. So helium, the first energy level is the 1s, and there's no p orbital on the 1s level. So helium is a 1s2. It has completely filled up its energy level. And there is a certain stability there that if it were to lose or gain an electron, it would not be as happy and stable as it is when it's nice and full. Neon it fills the 1s level completely, right? It's 1s2 for neon. So this is helium. Here's neon. Neon has filled the 1s2 level, and he fills the 2s, right? He has both 2s electrons, and he has all of the 2p electrons, 2p6. And he's fully filled in that second energy level. If he were to gain one extra electron, he'd have to bump it all the way up to the third energy level, which is a big jump in energy. But if he were to lose an electron, he wouldn't be completely full. And there's this stability associated with filling up that energy level. You do the same thing at argon and krypton and xenon. They are all at the end of their row. They have all filled up that level with electrons. So typically, if you look at like the second two rows here, 1, 2, 3, 4, 5, 6, 7, 8, there are 8, 1, 2, 3, 4, 5, 6. I drew an extra row. There should only be 6p. Anyway, there should be 2 boxes in the s orbital section, and there should be 6 boxes in the p orbital section, and that's a total of 8 outer electrons. 8 electrons on the outer energy level. And that's typically referred to by chemists as an octet. Octo, like octopus has 8 arms, okay? Octet of electrons. That is considered stable. If you fill up your octet, you don't tend to want to react with anybody. You don't tend to do chemical reactions. And you don't tend to change your electron structures. So a full sublevel is a stable sublevel. All right? That is what drives a lot of trends that we see on the periodic table. Now, if you look at atoms just on the other side of neon, now neon is number 10. Very, very stable. Doesn't react with anybody. If you look at this atom just to the left of neon, fluorine, number 9, fluorine is the most reactive element on the periodic table. To give you an idea, if you were to have a jet of fluorine gas, like a tank, let's say here's a tank filled with fluorine atoms, and you let those atoms out, you unleash the jet, and there's like a brick, the brick will catch on fire. The fluorine will react so strongly, it will rip electrons off the brick. It is super reactive. And it's just one away. It's almost full. It's hungry for those electrons. What about the next one after neon? Neon's number 10, sodium is number 11. Okay, sodium, just drop a piece of that in water and the water explodes. It catches fire. Sodium is very, very, very reactive, highly reactive, almost as reactive as fluorine. Fluorine we consider more reactive. And because if it just gets rid of an electron, it would be as stable as neon. So these two atoms will work as hard as they can, this one to gain an electron, this one to lose an electron, so that it will have that nice filled 10 electron second sublevel or second energy level. Okay, so we find that atoms that are almost there tend to be very unstable, and atoms that have gotten their octet are very, very stable. Now, let's do a couple of things here. As you go away from the edge, as you go from sodium to magnesium, this atom is not as reactive as sodium. It is reactive. It will react with water, for instance, but not like sodium. Sodium catches fire in water. Magnesium bubbles a little bit. Not as big a reaction. And when you go over here to, is that aluminum? Aluminum hardly reacts with water at all. It will oxidize a little bit over time, but it's very slow. If you wash a pure aluminum cooking tool, for instance, in hot water and leave it in the water for several minutes, you can get this dull coating of aluminum oxide. But it's nowhere near as violent as any of these two. And so they're getting less and less reactive as you go towards the middle of the periodic table. So there, likewise, if you go from sodium down to potassium, potassium is actually much more reactive than sodium. If you go down, if you took a little chunk of sodium, it might catch fire when you drop it into water. If you took a chunk of potassium and drop it, there's a huge flame, and sometimes it even will get sort of violent and explosive. All right, that's a thing we see. And if you kept going to like rubidium and cesium, those would be even more reactive with water. Okay. Well, on the other side, you kind of get a different effect. As you go from fluorine to chlorine, fluorine is super reactive, but when you go down here, this chlorine is not quite as reactive as this fluorine. When you go down to bromine, it's not quite as reactive as this fluorine. If you were to put fluorine across, a jet of fluorine atoms, like across the brick, it would get sparks and fire, and it would be very violent. If you put chlorine across the brick, you would probably get some discoloration. You probably wouldn't get a fire out of it. Okay, it wouldn't release that much energy. And as you go down to bromine, it would take a while for the bromine to react with the brick. So this is sort of a difference in vertical levels versus going horizontally. So we're going to talk about why we see differences in reactivity going left and right versus why we see differences in reactivity going up and down, with the knowledge that stability comes from filling your outer orbital. Okay? So I'm going to take a horizontal row. I'm going to take the second row, excuse me. So the lithium row. So lithium, beryllium, boron, and carbon, and nitrogen, and oxygen, and fluorine, and neon. Now, all of them want to be like neon, okay? So let's look at what happens as I move along the row here. Lithium, all of them have filled their first sublevel. This was the 1s sublevel. They all have those 2 electrons in the 1s sublevel. So as we go along here, lithium has a 2s electron. He's a 2s1. He has the first electron on the second energy level. Beryllium has that electron and another one. He has 2 2s's. Boron has both the 2s and now starts to fill a 2p1. And carbon is 2p2, and nitrogen is 2p3, and you can see where we're going. All the way up to neon, which is fully filled, and that's why neon is stable. I'm going to show you, again, I mentioned before the Bohr model. The Bohr model is not a super accurate model for multi-electron atoms, but I'm going to use it just the same here to give an idea, okay? Which is that the first energy level would be here. All of them have these 2 electrons on the first energy level. Lithium has 1 electron on that next energy level, and then beryllium has 2, 3, 4, 5, 6, 7, 8. Notice that as I was adding electrons to this ring, I was not changing the layers, right? This is all effectively like, you can consider it the same layer of electrons, okay? Whereas if I had to go to the level out, I would be adding a layer. But also notice that lithium had 3 protons, beryllium had 4 protons, boron had 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, and neon 10. Those protons are in the very dead middle, right down in here. As I was adding electrons to this second energy level, I was also adding protons in the middle. And you can think of those things as attracting each other. These protons are pulling on these negative electrons, like positives pull on negatives. So as I go from left to right, I am adding more pulling power into the center, but I am not making this ring farther out. The electrons on the outside edge that are being pulled in are all more or less at the same spot, same general area, energy level, cloud. So as I go from left to right, we see a couple of things. we see with more pulling power, we see that these electrons get pulled in closer. So the lithium atom would be maybe this size. The beryllium atom has an extra proton, pulls his electrons into here. The boron atom can pull his electrons into here, the carbon atom. And as we go to the right, we get smaller and smaller and smaller atoms because of how many protons there are pulling that layer. This could be considered the layer, the outer layer, pulling that layer inward. The other thing we see is that it becomes harder and harder and harder to remove those electrons. So it is possible with a certain amount of energy to take that 2s1 electron from lithium and pull it off. You can do that. When you try to pull it off of beryllium, it takes more energy. Well, you can imagine why. There's an extra proton holding onto it or trying to hold onto it, attracting it. When we go to boron, it's even harder to pull that electron off. So we would say that as atoms get smaller, it takes more energy to remove electrons. Okay? And they get smaller as you go in this direction along a row. This is often, when you ask why, okay? Some people ask, what is causing this? What's causing this? So let's say a because here. Because we would say the nuclear charge increases. Let's make this an actual sentence. Increases. So nuclear charge here, there were 3 protons. He had +3 in his nucleus. That's what a nuclear charge is. It's how many protons are in the nucleus. The charge on beryllium's nucleus is 4. That's 4 pulling instead of 3 pulling. That's a bigger nuclear charge. It makes him smaller, and it makes it harder to take his electrons. Boron, 5 nuclear charge. Harder to take boron's electrons. You can also start to see this, that lithium, we said lithium, and in general we said that the elements in this first row tend to be very violent, and the elements in this row tend to be very violent, right? Because they're very close. So they're almost full. Lithium is almost full if we take away his 1 electron. Well, he's also he has the weakest pulling power. It's easy to take off his electron. That's part of why he reacts so easily. It's because other things are very easy to react with lithium. Fluorine reacts very strongly as well, but he's almost full in the other direction. He's almost full by gaining an electron. And so he pulls really hard on other people's electrons. He has 9 protons in his nucleus. Really easy for fluorine to reach out and grab electrons, as it were. These guys in the middle are somewhere in between, right? They're not very close to the left-hand side, so they're not super weak, but they're also not really close to the right-hand side, so they're not super strong. So it's not as easy for them to either take or lose electrons, right? They've gained enough protons not to give them away easily, but they haven't gained enough where they can take them very easily. And when I start talking about taking electrons, I'm referring to a third factor here. So we've talked about two factors. We've talked about size, okay, as they get smaller, and we've talked about the energy to remove an electron, so let's talk about that. The energy to remove electron. To remove an electron, if you lose an electron, you become an ion. So the energy to remove an electron is called the ionization energy. Okay? But we'll talk about that separately from the ability of a single atom to try to take an electron. So fluorine, he really wants to steal an electron so he can have 6, so he can be like neon. And he's very strong. Okay, fluorine can reach out and grab electrons because he has so many protons on his energy level. On his energy level, on this row, he has the most protons other than neon. So he's what we would say the ability to take electrons. Let's define that. The ability to take electrons is called electronegativity. It's a big old honking word. So we would say fluorine is very electronegative, and lithium is not. Lithium has the least amount of protons on his row. So compared to fluorine and everybody else in that row, lithium is weak. Strong versus weak is a fairly decent way to describe attraction to electrons. If you have more protons on a given energy level, you will attract electrons more strongly. Now, the exception we could say is neon. Neon has the most amount of protons. He has 10. He pulls very hard on his own electrons. Now, technically, that means he might pull very hard on everybody else's electrons. You might think, oh, neon could steal very easily. But he's full. He doesn't want more electrons. In fact, putting more electrons in a neon atom would destabilize it. So we say that the noble gases do not have electronegativity at all. They are small, right? They will get smaller and smaller and smaller as you go left to right because they have more protons holding and pulling their outer layers in. So they have low atomic size. They have a high ionization energy. It takes a lot of energy to try to get rid of theirs. In fact, he has more ionization energy than fluorine. It's much harder to take an electron from neon than fluorine because he has that extra proton. But he's not more electronegative than fluorine because he does not want to take an extra electron, or that would put him over his limit. It would overfill his shell. It would have to bump up to the next energy level. All right, that's a row. What about a column? Let's do a column. And I'll do the sodium column, the lithium. So lithium is on the left. Underneath him is sodium. Underneath him is potassium and rubidium, cesium. If I draw lithium, lithium is remember, let's do this. This is 1s. This is 2s1. I guess hydrogen is in there too. 2s1. Sodium is 3s1 because he's on the next energy level down. Potassium is 4s1. Rubidium is 5s1, and cesium is 6s1. Okay. Well, lithium has two energy levels. He fills the first one with 2 electrons, and he puts 1 electron on the outside. Sodium has 3 energy levels. He fills the first one with 2 electrons. He fills the next one, 1, 2, 3, 4, 5, 6, 7, 8. And then that last, there's 1 electron on the third level. And I know I'm drawing a Bohr model, not an orbital diagram, but it still holds for the orbital diagrams. If you go to potassium, you can imagine 1, 2, 3, 4, and there would be 1 electron again on the outermost energy level. And for rubidium, you could keep going. Rubidium would have 5 rings, cesium would have 6 rings. So, what's happening? Well, here, definitely these atoms are gaining protons, right? Lithium has 3, sodium has 11, potassium 20-something, potassium's 39, etc. Okay, they're gaining protons in their nucleus. And you might think, oh, well, those more protons, they pull harder. But what they're also gaining is layers of electrons. So I want you to think about lithium's 3 protons. Lithium's 3 protons will try to pull on this outer electron. Think about the outer layer only. The outer layer is the one you got to control. Okay, so the 3 protons pull on that outer layer, trying to pull it inward. They are shielded, though. There's this inner layer of 2 electrons that gets in the way. Sodium has 11 protons, way more than lithium. But think about it. He has 2 full layers of electrons in between those protons and that outer one, and those get in the way. Okay, this potassium atom with all of his 39 protons has 1, 2, 3 layers of shielding through which that force has to, pull for the outer ones. Those shielding layers get in the way. And that's a bigger effect than just having more protons. So if you're worried about periodic trends, what we would say is that shielding has a bigger effect. Layers of electrons have a bigger effect on all of those trends I just mentioned than the total number of protons in the nucleus. So lithium is actually small, and sodium is bigger, and potassium is bigger, and rubidium is bigger, and cesium is gigantic. Okay. That would be a size trend that we see going from top to bottom. Well, What about energy? We said that small atoms, it's harder to take their electrons, and big atoms, it's easier to take their electrons. So lithium has compared to these guys, a very high ionization energy, and cesium has a very low ionization energy. And this is why when you dump potassium into water versus sodium, like I said, sodium will catch fire, potassium will explode. Okay, it's much easier to get that electron off of a potassium atom. And water will do it. So the reaction you're seeing is water ripping the electron off of these guys. Well, it happens much faster in potassium because potassium is so much bigger. It takes so much less energy to remove. That electron is just not as protected as it is in lithium, not as shielded. So we would say for the same reasons in the row, as the size gets bigger, the ionization energy decreases. What about the electronegativity? That's your ability to take somebody else's. Well, lithium, again, very small, and his layers are not getting in the way. It is easier for lithium to steal electrons than it is for cesium to steal electrons. So we would say small atoms, make that a sentence, have higher ionization energies. It's harder to steal from them, and higher electronegativities. It is easier for a small atom to steal someone else's electrons than it is for a big atom to steal someone else's electrons. Okay? So lithium is small, it has a higher ionization energy than cesium or anybody below him, and it has I say smaller than these guys, and it has a higher electronegativity than anybody here. If we combine those two things, okay, we get bigger atoms going from top to bottom, but we get bigger atoms going from right to left. So, taking a whole periodic table into account, where's my whole periodic table? What we would see is this trend. Big, small, little guys up here that have a lot of power, big guys out here that don't have a lot of power or a lot of strength. Okay? Little guys take, big guys give up. Noble gases are sort of the exception. Noble gases will be small. They will follow the size trend. It will be hard to steal from them. Okay, it will be hard to take their electrons, but they will not take anybody else's electrons. Helium is got an electronegativity of 0. It doesn't take electrons from anybody, but it is also the hardest to take from. You cannot steal helium's electrons hardly at all. In fact, I don't think there are any known helium compounds out there. Okay? That sort of explains why on this side, as you go to sodium to potassium to rubidium, they get more and more reactive, right? Because they're getting bigger and bigger and bigger, which is weaker and weaker and weaker, easier to take from. On this side, as we go from fluorine to bromine and down here to iodine, you actually get less and less reactive. Well, that's because this is the strong guy and you're getting weaker and weaker and weaker. So the other trend you might talk about is that atoms at the edges of the periodic table are either so weak that it's easy to steal from them, or so strong that it's easy for them to do the stealing. And the transfer of electrons is what we're going to talk about when we get into chemical reactions. So that's what drives chemical reactions is electron taking or giving up. Whereas the guys in the middle are a lot less reactive because they're not extreme. They're not either extremely weak or they're not either extremely strong. Okay, and to give up an electron or to take an electron, you have to be one of the two. Okay? All right, I know that was a long one. Thank you for listening. That was periodic trends.